Right. Hello, everyone, and good morning, good afternoon, good evening, wherever you may be in the world. Thank you all for joining us. I am happy to have two uh, esteemed individuals here to help me present on this topic today to talk a little bit more about cloud native geospatial, and more importantly, how it's more than just big data and how to use cloud native geospatial in your organization and some of the benefits that you can use. So that's our topic today. Before we get started, a few things as always. If you have any questions, you can ask those. There's a Q&A module. It should be at the bottom where you can ask a question there. Feel free to use the chat as well. If you want to just ask in the chat, you can do that there too. I'll be keeping an eye on questions, so I'll try to pop those in as they fit in with the conversation today. And then as we get started here, if you just want to drop in the chat, let me know where you're joining in from. I always like to see where people are in the world and kind of what they're doing. So if you want to drop that in and maybe, kind of a little bit about what brought you here today and why you're interested in this topic, that would help us and kind of drive the conversation. But with that, I know people will still be continuing to join in as we get started here. But I think we're already like about 1 minute in. I wanted to just open it up for some quick introductions, and we can kind of start from there. So, Amy, if you wanted to, if you don't mind going first, if you want to give a quick intro about yourself, your background, and some different things like that, we can go from there.
Yeah, thanks, Matt, and thanks for having me today. I'm Amy Rose. I'm the CTO of Overture Maps Foundation. My background is I'm a trained geographer, so hopefully that's a natural fit. I've been in geospatial my entire career, going back a few decades, but the main thing that I've always been involved in, no matter what domain or what sector I've been involved in, is data. And so seeing the trends and the transition into new technologies, particularly cloud native geospatial, has been really exciting. And so I'm glad to be able to talk about that today.
Yeah, awesome. And Eshwaran, if you want, I'll kick it over to you.
Yep. Hi, folks. I'm Eshwaran. I'm the CTO of Dotlas. We're essentially a company which brings together a bunch of information about restaurants and kind of gives it back to them in terms of insights and essentially helping with use cases like how should you be pricing your menu? Should you be offering a discount right now? What is the competition doing on certain ads and maybe on social media? And essentially giving this holistic view of the market to these restaurant operators so that they can make better decisions. That is honestly one of the best parts about this role that I love, essentially helping to, well, make those decisions happen. And geospatial is something that I've been working with for probably not more than 5 years, but it's been very cloud native first, very much in terms of the vector data sets, more so to represent the market for our use case.
Awesome. Thank you. Well, I wanted to get started by talking a little bit about kind of starting with the term cloud native geospatial and understanding or maybe breaking that term apart. I think as I've started to talk more about it, use it more, um, one of the big things is I've noticed that people kind of fall into two camps. They're either creating and generating and building cloud native geospatial data sets, and there's a whole component behind that, or they're consumers of those data sets, like they're actually getting access to that. But I guess what I would want to start with is if you can kind of provide your definition of what you think cloud native geospatial is and how you start to how you think about that, right? I mean, I certainly have mine, but I'd be curious to hear from your perspective how you define that and how you see people interacting with it.
Yeah, so I think the way I define it is more along the lines of how it changes how you work. So cloud native geospatial really breaks down a lot of the barriers, the data silos, and the barriers to interoperability that we've had, not just in terms of data, but particularly geospatial data. And so the way that the industry has worked with it in the past and necessarily through different formats, I think the way that I think about cloud native geospatial is a way to break that down, and not necessarily in a way that we have to everybody has to go to the cloud and now everybody has to change their entire workflow and the way they do things, but as a way to open up access. So open up interoperability and open up access to data.
Yep, likewise. I mean, the ability to democratize this to, your colleagues as well as, potential consumers, as you said, Matt, is a huge deal. One of the main things that I look at is essentially having a certain confidence at scale that comes with cloud native, because we can work on millions of rows one day, and then we're dealing with a data set which is probably tens of millions or hundreds of millions later, and we would know that it would just scale based on the compute and the storage that it is essentially using. So you don't have to worry about, okay, would it fit into my computer? Would it fit into the software? Does the team have to upskill on certain things, or can they just work with some of the syntax and everything just runs on the cloud? So very abstractly.
Yeah. So two big questions I had to kind of think and kind of to break down the concept. Number one, is cloud native geospatial just for quote big data?
No. No, I mean, I think from the perspective of being able to be much more flexible in how you build your workflows. And, again, technology is changing very quickly. Workflows are having to adapt very quickly. And typically, I mean, I found my entire career that when you start working with data, you might have one intent, but it quickly snowballs into something else. And that could be something bigger, that could be something different. And so, it doesn't have to be big data, but whatever you start with, if you start with cloud native, that gives you that flexibility to really, whether it's scaling or, being able to have access to a huge toolkit of different services to interact with that data. It gives you those collaboration points because of the data access right out of the gate. And so it doesn't have to be big data. And I think that's maybe when people think about it that way, that's maybe a limitation. It's really a way to get up and running and manage services, kind of like that low overhead, regardless of what data you're working with or what you think the future of that workflow is going to be.
Yep. I think so too. I don't think it's restricted to big data. I think, when you're a small company trying to work with a large amount of data, iteration becomes a huge deal. So the ability to already be cloud first and then take a small data set and then run some operations on it and then scale those transformations up, both of them work on the cloud, I would say approximately the same way, at least from your developer's point of view. So yes.
Yeah. And on the same token, the term cloud, I don't feel, I have heard from people that if, when they approach that term, it feels like, oh, I have to be in the cloud, right? I have to use tools that are cloud based, cloud processing, whatever that is. How do you attach the term cloud and to the term cloud native geospatial? What parts are required to be in the cloud, or are there any parts to be required in the cloud? And how do you where does cloud fit into all of this? Because I also think that sometimes cloud can be synonymous with cost, right? You do cloud services aren't free, or at least I don't know of many that are. So there is a component of cost associated with this that that can people start to think about, right? And of course that enters their mind. So when you add the term cloud into cloud native geospatial, what does that mean for you, and how do you think about that too?
Well, I think the way that I would think about it is using the best tool for the job. So, whether you're like, for example, Overture Maps, we store and process a lot of our data in the cloud out of necessity. It is the right tool, it is the right place to do it because of the highly collaborative environment, the access to a variety of different data sets, both in terms of, import and analysis. So there's a lot of reasons why we do that, but cloud might not always be the best tool for what you're trying to do. So for example, you might want to access data that's stored in the cloud, but the tool that you're going to use it doesn't necessarily need to be, cloud service for analytics. You can, use anything from DuckDB to, your desktop GIS to, Postgres to whatever tool that is the right size for what you're trying to accomplish. And so I think the cloud part of cloud native geospatial is really more about, hey, here's this additional environment that can help you build out your workflows in ways that support a specific use case. A lot of that, yes, is definitely storage, but for actually processing, and running distributed workflows, large data sets, cloud services and being in the cloud and running that in the cloud is probably the way that most folks would want to go.
Yep, pretty much. I don't think that cloud necessarily has to, be tied to something like AWS, GCP, or Azure. It could be anywhere as long as I guess it's accessible for your team and so on. It's obviously much better to run it there because the fault tolerance and scaling up the modularity is much better. But yeah, I think the core idea is just accessibility. So anyone of your team or any of your colleagues, how can they freely access this compute and storage wherever they are without having to, I guess, jump through hoops. So yeah.
Yeah, I think that's a great point about the access is, what that's one of the primary things that the cloud gives you, right? You can access the data in a variety of ways, and it's transparent to the user where that data sits, which is a huge step forward in terms of the way that we have traditionally worked.
Yeah, and especially when we're doing like when you want to read or and this is a topic that I've also been thinking about a lot is read forward workflows where you need to read a lot of data versus processing forward workflows. And when you do want to read a lot of data, I mean, we've we being geospatial, I mean, we've been using cloud for a long time, right? Open data portals are in the cloud, right? When you're getting data from somewhere over the internet, that's some sort of cloud, right? Be it wherever that might be. Um, but what's inefficient about that, in most cases, is bulk data downloads. Downloading gigabytes of data that need to get transferred over, or sending over a CSV dump. And I'm sure if, as both of you are data providers and data creators, you can understand the pain of that. What I, what the cloud, for me, what cloud native geospatial enables is two things. One is the ability to read that data more efficiently, right? Built into these files, be it raster data, be it vector data, whatever that is, there's a certain amount of efficiency when you're requesting that data. And I can filter it, I can retrieve just the bits I need. And the tools and increasingly more tools are supporting this to actually make that process much more efficient. So if I just need data in my neighborhood or my city or my county or my state or my province or my country, you can go and get that at that scale that you need. You only need to be selective about the bits of data that you need. And that's one big leap forward that I don't think we had, because previously you just had there's a great example is that there's a wonderful 1 foot DEM raster data set on the New York City Open Data Portal that I think zipped, it's about 23 gigs. Unzipped, it's about 121 gigs. Um, that's a perfect example of something I'd like to query remotely and use as a cloud native geospatial data set. But that's kind of the first step. So one of those key benefits, as of course, I think if you're producing data, is allowing people to selectively access that data. But on the flip side, when you're creating this data, right, and building it or updating it, what does it mean to be able to kind of, if you're creating an update and maybe it's a small update, maybe it's a large update, and being able to process scalable or scalably. What does that look like to do scalable processing on cloud native geospatial data? And what does I want to demystify some of that part of it too when you're actually processing. What does the elasticity and scalability look like? How do you kind of solve those challenges?
Yeah, I mean, one of the things that I like about kind of what you're touching on in terms of being able to access and read this data easily is the idea of partitions, right? So if you take something like a county, a city, a neighborhood, or you can just get a filter for any of those, it ends up being a narrow transformation, meaning that it just has to go and look for a particular file and send it back. One of the small advantages, which I have to mention again, is because the smaller partitions can still be loaded onto something like Excel. Not ideal, but it is what it is. But yeah, in terms of the larger partitions, I think it's very crucial to. I think of them as narrow and wide transformations. So all of this data that we're pulling, are we doing a lot of aggregations, or does it require everything does every node need to know what's on the other node, or can it just work by itself? And of course, there are parts of partitions that allow that and don't. And maybe one last point about the reading of the data that I think is sometimes relevant as well is based on how you partition, I think you or the requester incurs that much of egress, which really affects analysis. So, if I have to keep reading gigabytes of data each time to do some simple checks, then is that really blowing up the bill? Which should not be the case with good partitioning. So.
Yeah, I think I would add in terms of reading the data, just kind of a contrast between, kind of the way traditionally we thought about it and what gains we get now. And so I remember a conversation about a year ago, and somebody was talking about we should distribute Overture data packaged as particular countries. And so the idea there is that's what people are normally looking for is a some data that is by country or by city or by some particular boundary. And the interesting part of that is the way we also work as practitioners is a lot of exploratory data analysis. We want to look at the data, we want to play with it a little bit, and we might find, oh, this is great, I have this country, but I'd really like to see what's just on the other side of that, human-made boundary. There's nothing physically that is actually a barrier there. I'd really like to see the data on the other side. If you think about the way that we've read data in the past, and your example, Matt, is a perfect one, where you go to a website and you download some data. I download the data for the US, and I'm like, okay, this is great, but I'd really like to see what's on the border. Now I have to go back and I have to get all of Canada, and the reality is maybe I only want to look at the border to begin with, and I could have just done a request to that data to get a bounding box, or to narrow down my search to something that wasn't necessarily that's actually a spatial definition instead of an somewhat arbitrary definition and how data is packaged. And so that really helps that kind of EDA, that exploratory data analysis, that iterative workflow that is kind of inherent to the way we work in geospatial. And so I think that's a really important aspect of this. When people think about the ease of getting data, traditionally we thought about, well, I'd like it prepackaged in these chunks of things that I recognize as the right bin of data. But the reality is that bin rarely works anymore, particularly in kind of global scale, cross-border types of things that you're looking at. And we really need to start thinking about, actually, it's easier to be able to just very quickly say, no, I'd like the data in this bounding box. And if you look at it and say, wait, that's not what I want, you haven't downloaded, just re-query it, adjust your query. Now suddenly you have a new view and you're off to the races. Matt, you're muted.
It was, my chair is squeaky, so I spared everyone that noise. I think that, I mean, it's logical to the way that we interact with data, right? When we're thinking about a problem in geospatial, we're thinking about it spatially. We want to understand that in a context of a place, and that requires a different data structure built into it. When we're, let's take GeoParquet files for a moment. When you're creating those and building those out, being able to quickly eliminate lots of data you don't need. And I can ignore that. That's built into the file structure itself with row groups. That's built into the bounding box, that built into the partitions, all these things that I think are like kind of newer terms for, the geospatial community that may have worked in, well, unless you've worked in a database, things like a shapefile or a geo package or stuff like this, or these traditional methods of data delivery. They help you. To me, it's basically like filter out what I don't need and focus on what I do need. And the mode you answer that is through spatial questioning. On the flip side, a lot of these data structures have been used for a long time in the non-geospatial data world, right? And I think there's um, a huge push, and I think it's essential for us to make our data more useful and easier to interact with the broader data community. So I'm assuming that well, I'm not assuming, but I know that there's a lot of these tools that have been used for a long time outside of the the non-geospatial world. And how do some of these new formats or the data catalog systems, be it Apache Iceberg or Delta Lake and things like that, how does that make it much easier to bridge, the gap and deliver or provide access to data for the non-spatial community that wants to ask questions of spatial data? How does that, I guess, increase deliverability, break down any data silos, and as data providers, how do you see people actually interacting with that from the, the not the non-spatial world? As much as I don't want to divide it and split us up into two different groups, what is that? How do you see that as data creators?
Well, I think that's a great point. I'm firmly in the camp of spatial is not special. So I think for a while, certainly, years past that made sense as a statement that spatial was special. Now, I think what it does is it limits the usability, not necessarily because the data is not useful for non-spatial practitioners, but because it made it seem like this is something I don't know how to work with, or this is something that, I don't have the tools for. I think particularly now with, native support for spatial data types and things like Iceberg and Parquet, I think what it does is it makes that integration seamless. It makes it, transparent in a way that people who haven't worked with spatial data before don't look at it as some unknown, what is this? What am I dealing with? It's a, there are specific data types that are well explained, well documented, they can use. There are specific operators that are well documented. And I think what that does is it opens up the possibilities for really expanding, the use of spatial data in a way that people just haven't been using it before. I mean, we are a location-driven world, society. Everything is, has something to do with location, even if it's tangential. And to think about the ability that these types of technologies now allow, non-spatial people to integrate. You don't have to make a map. You don't have to, have a visualization. You can use spatial data the way that you've used any other kind of data in the past for business intelligence. And thinking about spatial data that way, I think sometimes when you're a purist, you think, well, we need a map. We have to have a map. The map is the thing. But the reality is that the data is the thing. And yes, you could make a map, but you should be able to work with spatial data the same way you work with any other data type. And now this technology makes that possible and easy and, trivial.
Yeah, absolutely. One of the major things that I find very powerful in terms of geospatial adopting these file formats and their access is to do with being comfortable with the file structure, right? Like if you're coming from running GIS solely on your desktop, you're probably used to organizing stuff into files and folders. When you go to something like S3, things are again in the object storage, still files and folders. And even better, when you have something like Iceberg or Delta Lake, you now have an SQL interface on top of your file structure. So it's almost like you have the flexibility of just adding files, split them up however you want, put them in there. And you can still, if you just want to read the files directly, go for it. If you want to have an SQL interface, if you're used to something like a PostGIS or SQL query-based, geospatial query-based access, go for it as well. I think that's extremely powerful.
Yeah. Yeah. How do you find most people that are interacting with your data from maybe that are not your non-traditional geospatial roles? How do you find people interacting with that the most?
Mostly, it's usually like something you post on an S3 bucket. It could be either a partition file or a single file. Single files are quite hard to work with because you have to, well, make it available, and then usually folks are downloading that, but then they probably try to load it on their computer. It happens. So essentially, it just revolves around putting it into someplace on the cloud. Could be S3, could be Google Drive, somewhere else, and they pick it up from there. There's no indexing or partitioning that usually goes into that. So yeah.
Yeah, awesome. Um, and the same token, how I do get this question a lot. It's kind of, looking at the compatibility with existing tools within, the geospatial ecosystem or the GIS ecosystem. Specifically looking at your desktop GIS, which I know is the most probably widely used amongst people that work in, your GIS sector. Are these still relevant with cloud native data? And if so, how? I
Yeah,
have my opinion, but I want to hear yours. So,
yeah. Yeah, absolutely. They are. I mean, your desktop GIS is just a different way of working with the data. It's a different tool in your toolbox. And a lot of people use that kind of interface. And I think that maybe the presumption is that no, there is no compatibility, but the reality is that ArcGIS, QGIS, they have support for cloud native formats built in, and so you can easily use those formats right in your desktop. It reminds me of when it was a big deal when ArcGIS started supporting SQL Server and Oracle connections, and an even bigger deal when they started supporting Postgres connections. And at the time, it was like, oh, this is amazing. And I think it's very similar when you have technology like cloud native formats that are really incredibly valuable. The ecosystem of tooling will build up around them. And so it's no different with kind of your desktop GIS. In fact, it makes sense to be able to make that desktop connection in a very direct way to kind of all the data that's in the cloud. So yeah, if you're a user of QGIS, ArcGIS, any desktop tools, those already have support for cloud native formats, and I think that's a really great way to start breaking into how do I use these formats? What are the differences? What are the things that I should be aware of if you want to explore that more?
awesome. Yeah, I agree very much. I mean, I think if I had to, and I always try to draw a parallel to the rest of the data world. I mean, it's no different than a BI tool, be that desktop or cloud or whatever that is. I mean, these tools for years have connected into a many different data sources, and that a lot. I mean, one that works really well with that is there those the cloud native cataloged data formats and things like that. So I think that works really well. I wanted to shift into the topic of data conflation, and you're both experts on this, and I'm not. So I'm interested here in this topic too. Is how do you actually use multiple geospatial data sources that you're bringing in? And I'm sure this is a problem for many organizations out there. Um, you're collecting data from multiple sources. How do you bring this all together to create a new data set? And what are the challenges of that? Managing different data sets and formats from different sources. How do you manage overlaps? What are the processing challenges when you deal with this? I mean, spatial joins are a complex thing, or looking at distance queries or stuff like that. I think probably one of the most like computationally intensive things I've done is trying to create a really comprehensive training set for like real estate data, where I'm doing, K nearest neighbor joins across multiple schools and looking at neighbor values and filtering those out, looking at and integrating with census data. I mean, I it created much more data from that, but it took a really long time to do that. And this was years ago. So I mean, something like that. I mean, and this is one small area, but like I doing that at a global scale, creating it consistently, having the right processes in place, and then managing like the versions of all of that. Can you break down that challenge as you have both put into place respectively for the data that you create?
Yeah. So, for us, it's really important for us to get a bunch of sources together to essentially present insights, right? So we really focus on, okay, let's say we're looking at a restaurant or we're looking at a brand in a particular city. Maybe it's a McDonald's, maybe it's a mom and pop shop, right? Various sources, whether it's online or offline, whether it's, you got it from crawling, maybe you got it from the United States, census in terms of some of the statistics they release, maybe some other places, right? So, we have a very rich variety of sources, in 2025. So bringing that together so that there's that holistic view when you look at a restaurant or brand was very important for us. So how can you know when you look at a restaurant in terms of, okay, what kind of menu does it have? Is it missing on certain things in certain places? Does it price differently, on different sources? Is it, do you get a special discount if it's from the restaurant's own website? Is it different if it's from a food delivery service and so on, right? So to get to that holistic view, is quite difficult, I have to say. It's definitely one of the more tougher problems I think I worked on personally, but it essentially comes down to divide and conquer, I think, in terms of, okay, how can we essentially negate everything that is not related to a particular data point when we're bringing stuff together. There are some formal terms for this. Usually they go with record linkage, entity resolution, and so on. But at least in the geospatial format, it's all about, okay, if there are multiple sources of data that represent restaurants in a city, then how can you bring all of them together into a single unified deduplicated data set? And here, deduplicated doesn't just mean, you have duplicate rows per se, but it's duplicated across sources, right? So bringing that together. So yeah, one of the ways that we achieve that is really just by, I would say, I would think of it something similar to a binary search, which is essentially like, okay, what are we confident about? What are we definitely not confident about? So that would already solve 80% of your problem, right? In terms of what do you know is part of this? What do you not know is part of that is easy to eliminate until you get to the border where it's like, okay, this could go either way. And that's the region where you end up with a lot of false positives and false negatives. So now how do you kind of deal with that is a bit more contextual, I'd say. There's a combination of curation that goes into that. There's, with LLMs, there's a lot of help to be had these days. And of course, statistically, you can actually use some methods to assign certain things as being more confident as a match or, not a match. So, yeah.
Yeah, we do some very similar things. Our pipeline right now, we're, I guess, importing about 200 or so different unique sources for all our theme data that comes through. And what we were trying to do, in a big part because we want to both preserve data source feeds, but we also want to make sure that we're tracking data provenance, is that we've set up our pipelines to ingest feed data and then go through what we call a match, store, merge process. So we're doing all our feature matching before we do any kind of actual conflation to get to a single feature that comes out in our releases. And, I think the two big things here, certainly excited to see native geospatial support in Iceberg for, is that we really need that for versioning, and we also need that for rollback. So you think about the process of a match merge store, there's things that you're dealing with, like you mentioned, duplicates. That's a big one, both in terms of coming in a source feed, but also once you get to the matching process. For the source feeds, we want to be able to, do either bulk or incremental ingest of data from, any cloud buckets, S3, Azure Blob Storage. But we also, hit APIs, things like open addresses, to ingest data that way. And it makes it a lot more seamless to be able to hit APIs that way and ingest data. For the matching process, this is something that I think is really where you start to see the power of being able to work in cloud native and be able to work, kind of with the microservices that you have available to you. Because if you're talking about matching building features, that's a different process than talking about matching points of interest. And you might want to use different types of analytics services to be able to do one or the other of those. And so one of the recent things that we did, which was both necessary for that kind of scenario, but also because Overture members are coming from a variety of different organizations who all use different tech stacks. And, we had to kind of standardize on, what we call a recommended tech stack, which, some folks use, Azure Blob Storage, some people use AWS S3. Some people are using Databricks, some people wanted to use Glue. So we recently decided, we had a lot of different ways that we were approaching some of these things. Why don't we develop a platform agnostic Airflow DAG so that we could, send our Sedona Spark scripts through, the logic doesn't change underneath, but we wanted to be able to send it to any platform. And so what that enabled us to do is send the same scripts to different platforms, but it also allowed us to kind of test out new opportunities. So, for example, the buildings pipeline and particularly the intersection of all the buildings and the spatial intersect, and you can imagine the complexity of not just 2.3 billion buildings, but the intersection of multiple sources that produce those. We wanted to see, hey, is Glue the right process for this, or is there something better? And so being able to use that platform agnostic DAG allowed us to experiment with WhereaboutsDB, in fact. And you can see for buildings, we could get that optimization for those particular types of scenarios. It might not be the same way for points of interest. It might not be the same way for some of our transportation networks. But specifically for that purpose, we could very easily just reconnect our workflows to different platforms and using different services. So when we're talking about kind of real world workflows and dealing with big data, I think that kind of, that kind of architecture where you can really just pick and choose components and easily test out what is the right optimization for this type of feature, and can I make it in an agnostic way to where I can apply it to other parts of our pipeline. Very powerful.
Yeah, I like the ability to, and one thing I've really enjoyed is seeing how many places Parquet, GeoParquet, and eventually Iceberg and some of these different catalogs can go. I mean, you can take these very portable data formats in a lot of places. And the orchestration is pretty lightweight. You can create Airflow pipelines to do these things, and then you can give it to so many different people to take it into whatever they choose, right? It's not like, well, you're prescribing how they have to use it downstream. There was one question specifically on applying the GERS in cases like merging and administrative regions when resolving IDs to preserve while maintaining cloud native principles like interoperability, minimal data movement, stuff like that.
Yeah, so that's really a big part of our match store merge process. We match all features. So if we have multiple administrative boundary features from different sources that are specific to a particular boundary, we match all those first. So if we have 3 sources of boundaries for Australia, then we're going to match all those together and assign all the matches the same GERS ID. So what we're saying is, regardless of the source that this feature comes from, it will have the same ID as that same feature in a different source. All of that is stored in our corpus repository, which is large. So once we have that, then that gives us the ability to not just, we could pick one. We could say, sort and pick one, and there's your release. We could say, let's do some more intelligent conflation and think about, well, for whatever reason, whatever business rules, this geometry is accurate. But these attributes from this other source or these other sources are the ones we want to use in the release. Let's put those together. Or you could say, the license, even though they're all open licenses for all the sources, maybe a particular license is more permissive than another. So we want to flow that through to the release. And so that gives you a lot of opportunity to not just kind of be flexible in how you're releasing data, but also preserve the provenance of the original source feeds. And in fact, one of the things that we've just started to do, if you go out to our releases, is export what we call a bridge file. So what that has is all our sources with the GERS IDs attached. So, it's kind of that corpus dump for folks that are interested. So for features that didn't make it to the release because there was already a feature with that GERS ID that took precedent, this bridge file will have kind of the rest of the story.
Awesome. Yeah, thank you. That's I know it's in the documentation, but it's good to hear how it plays out and in a real world structure. I want to get to two pieces to kind of dig into, like, okay, how do you do this in IRL, in real life, and kind of what does that look like? And I think understanding, you're creating these large scale data sets. How are you seeing some of the kind of optimized performance? Where are you able to make these performance gains in these different tools using cloud native and different technologies? And then also kind of how is that changing in terms of cost efficiency? Because I know that's a big question in terms of, like, if you're making a leap to the cloud or you're exploring cloud technologies, what is that cost and performance are two big barriers, to understand. Is it like, how can I do this, be efficient, do all these things and still deliver something on scale? So I know I kind of wanted to hear how you are both doing that today, in terms of the data set creation beyond just the tech stack choices and things like that. But yeah, I kind of wanted to dive into that question, and then from there we can open it up to more Q&A from there.
All right. Could I use this as a segue to just share
Yeah.
a few slides? Yeah. Okay. Fantastic. Yeah, just a second. All right. That. Oh, I do have to rejoin, so maybe Amy can take this one for a second.
Oops. Okay. Well, I'll kind of fill in here. First, I'll say that I posted kind of the link to our GitHub page, and where it shows the recommended tech stack that really just factors in, how we want to think about putting things together without having, 1,000 different types of technology integrated into our pipeline. And actually, that's kind of a good segue into this conversation about costs and how we approach it. We have Overture infrastructure. We're running on both Azure and AWS. And depending on what part of the pipeline or what processes that we're working on, some folks might be working in either or. We want to be able to do, kind of cross-platform as well, obviously. And so a lot of the way that we think about costs is, kind of this testing approach, where we might have a particular process that we know that we want to run at scale. So we'll start small, look for ways to optimize that, look at the costs, look at whether it makes sense to have something that runs every day, every week, every month. What is the right runtime and cadence for those things? But also make sure that we're looking for ways to optimize. And so if you're thinking about kind of costs, again, going back to the right tool for the job, if you want to run on the cloud, it's great. It's a managed service. There's low overhead in getting started. But the reality is you might be able to just take advantage of, data being hosted by somebody else on the cloud and use something like a DuckDB to work with that. So it looks like, Eshwaran, you're up and running. I'll let you take over and then I can cycle back if needed.
No, thank you so much for that. Let me just try this again. Can you see my screen? I hope so.
Yep, all good.
All right, fantastic. So this is just a kind of a use case or our case study of how we integrated robots with Dotlas. And a few things to essentially know is that we primarily run on, Databricks. So, we're kind of the folks that Amy deals with that, has to, very persistent on a stack. But yeah, you can imagine this as being our AWS environment where our Databricks essentially runs. And this, series of, call it circles, is just representing various tasks as part of a pipeline. You can see that they are reading data through Unity Catalog and Delta Lake from the underlying S3 object storage and AWS. So various tasks essentially read and write back data to essentially Delta Lake and Unity Catalog, right? So all of this runs in Spark, and there's essentially one part of it, for instance, that could essentially use large-scale geospatial joins, for instance. So what happens there is let's say the data from this third task here goes back into Delta Lake, which is still underlying S3 storage, right? And we were able to integrate robots, which, by the way, work fantastically, which we'll see in a second, to essentially seamlessly just go and using the Delta Lake from Spark again, run the spatial join task, and we can essentially just poll that job just to make sure that things are going as intended, and then it essentially puts it back into S3 for the further tasks to take on with. The reason that this is very powerful is because it comes really much into cloud native in the sense that the data doesn't necessarily leave our AWS environment. It's still there. It's essentially just a compute which comes in, which is very powerful as part of the Sedona and the way the robots will optimize that. If we go into this is essentially what the spatial join kind of looks like. You can just imagine this is a map with the various points here being restaurants, essentially restaurant locations, and they being from various sources. So, color red, green, and yellow, blue, for instance. So one of the things that we use is the D within, which essentially means, okay, taking this red point, for instance, find all similar restaurants which are nearby, maybe within a 250-meter radius, right? And what essentially comes there together. So what are the nearby restaurants? And the kind of assumption here is that, whatever you're trying to match in terms of the same restaurant from multiple sources, they are probably very close to each other. So really based on the kind of radius that you can take a bunch of nearby restaurants for any source, and then assume that they're going to be part of the kind of total universe of restaurants that you have to check to make sure that it's part of the same physical restaurant, so to speak. So, as part of as Sedona syntax goes, it's quite easy. If you probably come from something like PostGIS or just working with Geospatial SQL, this is going to look very familiar. You just pass in the geometries, in this case, the points and the radius, and you essentially can get to work. So it was definitely quite powerful. But really, most of the power came from how fast this was able to run, right? So before we were on Whereabouts, we still had this use case, and we used to use BigQuery. And this was to, for example, on the United States countries level, we had a bunch of sources that had restaurants, right? So maybe there was a single online source that had 850K restaurants, and another one that had a lot, maybe some had very less. But the idea being that we had to bring all of these together, right? And essentially at the end of that matching process, all of these can kind of conflate, as we were talking about, to 1.1 million restaurants. But one of the starting steps to that is to find the nearby points and then figure out how the matches work. So when we were doing it in BigQuery, we had to put data into GCP. So it was very, I guess, kind of it was a bit prickly. It was like, oh, why is data, leaving this environment and system? Why doesn't the compute just come here, right? But still, and another thing is we had to partition by state, meaning only process each state individually. So, any restaurants that were at the border of two states were instantly, primed for mismatches, right? And of course, we could essentially run multiple states concurrently, and we could, well, do a bunch of source comparisons. In this case, we were using on-demand, so not the dedicated slots with BigQuery, and this took a lot of time, right, just to process all of these restaurants and kind of do that operation we saw on the previous slide about just finding nearby restaurants. Was about 4.5 hours, so quite big. So when we essentially switched to whereabouts, which again was, where, as you saw with the previous, again, that slide, the data still resides here. So the compute is able to use it, it processes it in memory, and then it essentially is putting it out. And here we don't have to process by state, and we can partition it any way we want. It's going to be much more flexible. And then we end up with about an 18 minutes runtime, which is just significantly better. And again, kudos to the whereabouts team. They were a huge help, both in terms of helping us get it set up with this, as well as what's essentially being built here. Finally, that essentially helps us end up with a beautiful restaurant map that looks like this, with all of the over 1 million restaurants in the United States, which are matched by source and with the various features. So I'm just gonna kind of leave that there.
Yeah, I mean that describes it perfectly, where there's that, flexibility that allows you to scale it the way you need to. And then, you can add enhanced performance in the places you need, and have those benefits, which I think it exemplifies that really nicely, going through those different pieces there. So kind of to, bring it together here. And if you have, for everyone watching, please add your questions to the Q&A, because we'll crack that open here. Any kind of parting thoughts that you want to kind of leave the discussion with? I think we covered a lot in terms of, cloud native geospatial isn't just for big data. It enables lots of different things. It allows you to, you don't have to have the cloud, right? You as a user or reader of that data, that gives you benefit, but it brings data to a lot of other places. It's going to break down the data silos. And I think it allows you, as if you are creating or processing data, a lot of flexibility in your choice, and allows you to bring that data to many more places. But any other kind of final thoughts? And then we'll open up for some other questions here.
I think I would just say, if you're new to cloud native, a great place to start is just start working with cloud native formats. I mean, there is data out there, whether it's in Source Co-op, Overture. There's a lot of data that's available with both raster and vector in cloud native formats, that just start working with it, whether it's in your desktop GIS, whether it's through something like DuckDB. If you write code, integrate it into your code, and start there, because I think that will get you more familiar with just how some of those structures work. And then it'll be much easier if you actually want to start using more cloud services to integrate that way. So yeah, I know this is kind of a fundamental shift in how we work. And so I think just starting with those formats is a great place to start and learn.
Yeah, I guess my parting thoughts would only be, whether you're scripting, with respect to the geospatial stack, or if you're, just using geospatial technology in general or not, right? If you feel like it's getting tedious or mundane, or whatever it is that you're doing feels somewhat off, or just too much work, then there's probably an easier tool for it somewhere if you just look hard enough. So.
Nice. I like that. I'm not seeing any questions at the moment, but if there are any questions, make sure to drop those in here. I think there was one earlier looking at raster data formats for ML training. Is it a good idea to move them to a different format, like a NetCDF or cloud optimized GeoTIFF, or other formats and things like that? In terms of, I guess, how we're looking at that at whereabouts, I can at least answer that, and then happy to hear, from both of you as well. But I think the key principle of cloud native is to leave data where it sits and be able to retrieve the parts of the data that you need. And depending on what you're doing with the the training and things like that. If you're using just parts of an image, or if you're using certain pixels or whatever that might be, you want to just retrieve those. And Cloud Optimized GeoTIFF does a good job of that. Of course, you have to have the right tools that are optimizing those reads so that you can read that data in. If that's a array-based format like your ZAR, NetCDF, things like that. There's different tools to work with those, so you can work over time series and things like that. But what I would try to do is, as much as you can, optimize the read of that data, and leverage things like overviews if you can. The Cloud Optimized GeoTIFF has overviews, so if you don't need the granularity of all these pixels in a certain area, you can go up a level and get your averages and things like that. So that would be my take on the raster side of things. But any other thoughts do you guys have?
Not necessarily. I'm firmly in the vector space right now, so
Yeah.
Same here. Sorry.
Yeah. Yeah, the raster one I've only started playing with a little bit recently, just with and to to be clear, like one thing I did when I was kind of first playing around with Sedona and whereabouts was grabbing all of the Overture buildings in the world and doing a zonal statistics with this like height above nearest drainage, like kind of reverse engineer DEM for things like where drainage and water go. And the fact that I can just leave 996 gigs of raster data on AWS, and then based on a small buffer I'm creating around every building, uh, perform the zonal stats and just grab the pixels I need. Having set up the right structure is really nice. Like that's just a really nice thing to do. But that's the whole point, is like if there's one building in the middle of nowhere in the whole tile, and I don't have to download that whole 512 by 512, pixel image, I just take the handful of pixels I actually care about and pull that over the wire. Then that's what makes life easy. Or fast or performant, however you want to put that. Okay, so I didn't see any other questions pop up in the Q&A. So for now, we can kind of leave it there, I think. But thank you both for taking the time today to have this discussion with me. Hopefully, we cleared up some different, I don't want to say misconceptions, but kind of clarified how we're seeing cloud native geospatial evolve. Thank you both for being, kind of leaders in the space and kind of taking the time to share this with a lot of the group here. And if there are any other questions, you can go ahead and follow up, and I'll make sure to pass those along. But thank you both, and we'll see you all next time.
thanks, Matt.
Thanks.
Cheers. Goodbye.
All right. Bye.